Alright, so our topic is the selection problem, which we have seen already, where the input is an array of n numbers, the array is unsorted, and also an integer k between 1 and n, and we should find the kth smallest number in A. So this is a problem, and we already saw a nice solution for this, which was the median of median algorithm, right, which could solve this in linear time, that is big O of n, which is already optimal, right? And this was a comparison based algorithm, which uses some sort of crazy divide and conquer strategy. And if you remember, the idea was something like this. We have an array A. So essentially we want to find an element which we call as the pivot in such a way that, let's say we want to find an element which we call the pivot. Pivot is equal to, let's say, x, an element in A, and we want to divide this array into two portions such that you have an A1 here and A2 here, right? All the elements in A1 you want it to be less than or equal to x, and all the elements in A2 you want it to be greater than x, right? Then we said if I'm looking for the kth smallest element in A, that is, let's say, select AK, I'm looking for the kth smallest element in A, then this can be written as the following, or this question can be reduced in the following question, is simply select A1 k if k is less than or equal to A1, right? If k is less than the size of A1, then that element is going to be in this array, and that is going to be exactly the kth smallest element in this array. And otherwise, you simply select the k minus A1 size of A1 element from the second array otherwise. So this is what the algorithm we had, which is a nice divide and conquer strategy. Then we had to find, the hardest part was finding a nice pivot. We wanted a nice pivot in such a way that the size of A1 and the size of A2 are, pretty similar. Ideally we wanted that to be n by 2 and n by 2, but we managed to kind of make sure that the size of A1 and the size of A2 is less than or equal to 0.7n. Okay, I'm just recapping what we have done in the previous lecture. Then we managed to come up with a crazy recursion like this, t of 0.2 plus, so essentially we managed to make a recursion like this, that is t of n is less than or equal to t of n divided by 5 plus t of 0.7n plus big O of n, which we solved using substitution method for solving recurrences, and finally we showed that this is big O of n. And it had a nice proof and some clever techniques. Yeah, so that was the main idea behind median of median algorithm, and we got big O of n, optimal worst case running time. So all of these things are great. Now what I want to show in this lecture is another algorithm, which is known as nothing but quick select. Okay, this is another algorithm for solving the same problem, and this is a randomized algorithm. This is a randomized, and more specifically this is a Las Vegas type algorithm, which means the algorithm will produce the correct answer, but just that the running time we want to bound in terms of the expected value. Alright, so this is a randomized algorithm and it is a Las Vegas type. And the running time is this big O of n expected. Okay. So one question you can ask at this point is, why should we even bother about this algorithm? Because here we can get big O of n, which is already optimal, worst case running time, and here it is big O of n expected running time. Okay. So with worst case could be even, bad, and in fact the worst case is n square. So one way I can answer this question is this. This is going to be a much simpler algorithm. That is one advantage of this, simplicity. And typically simple algorithms are going to be much faster in practice. Here we have a big O and there are going to be some, really bad constants in this. Here the constants are going to be much smaller. So in practice, with very high probability, this algorithm is going to be faster. Okay, so that is one way to convince you. And overall, this is a nice idea, and with some nice probability analysis, and let's see how it works. Okay, so what I'm going to explain now is how quick select algorithm works. Alright, so quick select also picks a pivot first, then it will partition the array into two subarrays and continue the selection in one of these arrays. The key difference is in the way we choose the pivot. So in the previous deterministic algorithm, we had a very elaborate procedure for getting something which can divide the array in somewhat balanced way. In the case of quick select, all we're going to do is just pick one element randomly. More specifically, we will pick one element uniformly at random. Okay, pick an element in a uniformly at random. So uniformly at random means the probability of picking any particular element is equal to 1 over the size of A. That is the probability of picking any particular element in A is 1 over A. Uniformly at random, and choose and call it as the pivot. That's it. So the algorithm is as simple as that. You just pick a random element and keep doing the regular stuffs. Okay? So now the challenge is, how do we prove that this works? In other words, how do we prove that the running time, right, the running time or the expected running time is bounded by big O of n? This is the challenge. Okay, the proof. Okay, so firstly let me define something called a good pivot. Okay, so here in my algorithm, what we are actually doing is we are going to pick an element randomly and call it as the pivot, right? So I will call that element a good pivot if it can partition this array A into A1 and A2 in a somewhat balanced way. So when I say somewhat balanced, I want the sizes of this A1 and A2 should be within a factor of 3. Okay? In other words, what I want is this: the size of A1 as well as the size of A2 should be bounded by 3 over 4 n. Okay? Which means both can be n over 2 and n over 2. That is allowed. Right? One can be 3n over 4 and the other can be n over 4, that means within a factor 3, all right? But you cannot have A1, the size of A1 being like 90% of n and the other one 10% of n. That's not allowed, okay? We want it to be somewhat balanced. In this case, the sizes will be within a factor of 3, okay? So if this condition is satisfied, then I will call the randomly chosen pivot a good pivot. Okay, so now what I want to ask is the following question. And another thing what I'm going to say is this. If the randomly chosen pivot is a good pivot, then I will call it a success. Okay. So success is, the definition of success is the following. The randomly chosen pivot is good. Then I announce success. So what is the probability of success? What is the probability of success when I pick an element randomly? And my claim is that this is going to be half. Why? Because if you visualize the elements in the array A as follows, let's say these, in the sorted order, okay, sorted order. That means you have somewhere here you have the n over 2th element, then somewhere here you have the 3n over 4th element, and somewhere here you have the n over 4th element, right? So now we are picking one of these elements randomly. Okay, the sorted order is just for the sake of illustration. I mean, originally this is not sorted. So now I am picking one of these elements randomly from here, which means I am picking one of this element randomly, uniformly at random. So which could be either this one, this one, this one, this one, any of this. So if I am picking, let's say, this number, then it is easy to see that this condition is satisfied, right? The size of A1 is clearly less than, this will be the size of A1, which is clearly less than n over 2, so clearly less than 3n over 4. The size of A2 will also be clearly less than 3n over 4. Similarly, if I am picking something from here or something from here, these conditions will be satisfied. However, if I am picking something from here, then this condition will be violated, which means as long as I am picking anything from this region, that is good. Okay, and the number of numbers in this region is n over 2. Therefore, the probability of success is n over 2 over n, therefore half. So that is how I get probability of success is equal to half. Okay, first time when I pick a randomly chosen pivot, the success probability is half. Essentially, probability of success is half, which is same as the probability of failure. Okay, so this is good. So now I want to ask the following question. Suppose I am doing the following thing, okay? Suppose I am doing the following experiment. I'll pick a number randomly, okay? And I will check if it is a good pivot. I can easily check if it is a good pivot by doing the actual partitioning, right? Which takes often time. So yeah, so I will pick a pivot randomly and I will check if it is a good pivot. If it is a good pivot, so first time I will pick a pivot, let's say P1. If it is a good pivot, then I'm done, okay? If it is not a good pivot, then I will discard the first pivot and pick another one. All right, let's say another pivot P2. Okay, if it is good, I'm happy again. If it is not, I will discard and pick another one, let's say P3. right? If it is good, I'm happy. If it is not good, then I will discard and look for another one. Let's say I will keep on doing these experiments until I find the first success. Okay, let's say I have done this experiment h times. Okay, and what I'm interested to know is what is the expected value of h, right? This h can be really big, right? H can be really big. H can be even infinity in the worst case. But in the expected case, what is going to be the value of h? Let's see how to compute this, right? Expected value of h is nothing but, right? So h is essentially a random variable, right? It is sigma for I is equal to 1 to infinity, right? The probability of first success at ith trial. So I can say something like this, right? You found the first success during ith trial. And if you do the math here, what you're going to get is this. The probability of you succeeding in the first trial is like, so 1 into, the probability of succeeding in the first trial is 1 into half. The probability that the first success is at the second trial is what? Right? The first success should be at the second trial. That means the first trial should be a failure and the second trial should be a success. That means half into half. Now 3 times I'm looking for the probability where the first success is a third time. That means the previous 2 attempts must be a failure and the third attempt should be a success. So 3 into half into half into half, or half cube. Therefore this equation will look like, I multiplied by 1 over 2 raised to I for I is equal to 0 to infinity. And if you do the sum, what you will get is going to be 2. Okay? If you do the math, you will get this as 2. Okay? In fact, even without doing all these calculations, I can say this is 2, because if you are doing a random experiment, okay, in such a way that you have, let's say, some probability p for the success and some probability 1 minus p for failure, then what I want to know is what is the expected number of trials I should try until I find the first success. That is going to be 1 over p. So this quantity is exactly 1 over p. Okay, so if you don't remember the details of this proof, you can actually have a look at the previous lecture on the basics, or on some probability basics. All right. But anyways, you can evaluate this and still you can get it, which means the following: in just two trials, I will be able to find a good pivot. Right? In just 2 trials, I will be able to find a good pivot in the expected sense, and I can partition this array into, somewhat balanced form. Okay, so just keep this in mind, and what I want to ask you is something else. Okay, so here what we did was, like, we tried to find a pivot, then if it is good, we take it. If it is not good, we just throw this and try to independently find a new pivot, right? That's what happened here. And I want to slightly change this experiment and ask you what is going to be the new expectation. Okay, so this is what it is. Okay, so here is what I'm going to do in the new setting. So new setting. Okay, so the first step is I have this array and I will pick a pivot X randomly, and I will split the array A into two parts, A1 and A2, A1, A2, and what I will check is the following. Is this a good pivot? I will see if the sizes of A1 and A2 both are bounded by this number. If it is a good pivot, then I announce success the same way as before. On the other hand, if it is not a good pivot, that means if the sizes are not, as balanced as I wanted. For example, suppose let's say n is equal to 100. So if it is 80 and 20, that means it is not balanced. So not a good pivot. What I'm going to do is, instead of finding a fresh pivot from this array, I will try to find a pivot from this array, the larger subarray, and try to split this again into two smaller ones. Okay, so this is my first pivot, so let me call this pivot as P1. Okay, so now I will find P2 because P2 is from the largest subarray. Now I will check what is the sizes of these two. I want to make sure that the sizes of these two, this one is clearly less than 3n/4, so I don't have to worry about this one, right? Because this is a smaller subarray which is less than or equal to n/2, so therefore strictly less than or equal to 3n/4. So, and this is a larger one, and I'm going to split this again into two smaller subarrays, and I will see how about the sizes of these things. Are they both? I want the sizes of this one as well as this one bounded by 3n/4. Okay, n is not changing, this is n. Okay, are they small enough? If they are small enough, I will announce success. If they are not small enough, I will go and find the larger subarray. So for example, if it is a split like, there are only 80 elements here, so 65 and 15 is success, right? Because 3n/4 is 75, and now when I see 65, 15, it's a success. But a failure means, for example, let's say 78 elements came here and just 2 elements came here. Then this is a failure. What I will do is, I will split this array again into two subarrays by choosing the next pivot from this one. Okay, so on and so forth. So this is what my new procedure is. I'll keep on finding these pivots. Again, let's say the pivots are, let's say P1 dash, P2 dash, P3 dash, etc. until I have all the subarrays at the bottom level are of size less than or equal to 3n/4. So suppose I find the success after, let's say, L trials. After L trials. And the question I want to ask is, what is going to be the expected value of L? What is going to be the expected value of L? Okay, so my claim is that the expected value of L is going to be less than the expected value of H, which is equal to 2. So I want to just give a kind of a sketchy proof, right? But that should be enough. So you can see here, in that case, the probability of success was always the same, right? All the events were independent, so the probability of success was always the same. So if the probability of success is high, that means intuitively the number of trials you need will be low, right? So probability of success is fixed here, which was 2, then the number of trials you needed was 1 over p, 2. Okay, probability of success is fixed for each trial. However, in this case, the probability of success is actually improving after every trial, right? Originally it is n over 2. It is n over 2. But if the first trial is a failure, then what will happen is you have only 80 elements here. You have 80 elements here. And you want the size of one subarray to be bounded by 75, right? 3n over 4n is 75. That means the probability of success in the first level it is half, right? But unfortunately, if we failed and we got into this sort of a, split 80-20, then the probability of success at this level is actually 75 divided by 80, which is much higher than half. So each time the probability of success is improving in this strategy. Therefore, the number of trials you will need to find the first success will be lesser than the number of trials you will need in this strategy, in the case of this strategy, in expected sense. Okay, so that's all I wanted to convince you, that this strategy needs only 2 trials in expectation to make sure that the size of these smaller arrays are bounded by 3 over 4n. Okay, so now we are almost done. So if you look here, our original Q select algorithm, this is exactly what we are doing, right? This is exactly what we are doing. We are finding a pivot, then we are splitting, finding a pivot again, splitting, etc., right? And we will continue the recursion in one of these arrays. And what this result says is the number of levels you need to go, the number of levels you need to go until you make sure that the size of a subarray is bounded by 3 over 4n is only 2 in expectation. Okay, in other words, what I can write is something like this. Suppose Tn is the time for solving quick select problem, then Tn I can bound as follows. T times 3n over 4. Okay, this is the size of a subarray with size bounded by 3 over 4n plus what you need is the following. The number of iterations you have to do to get this up to a smaller subarray. Essentially the number of, this is a divide and conquer strategy, right? So the number of divisions you need to do, number of divisions you need to perform so that you will reach here. You will reach to a subarray of size small enough, and this is roughly L times, right? L is the number of trials, and each trial will cost you a linear amount of time, right? Because once I find a pivot, I have to make a split. So L times big O of n. Therefore, if I'm trying to find the expected value of T of n, I can say that this is same as the expected value of 3 over 4n plus the expected value of L, which is bounded by 2 times big O of n. So the whole thing I can write as Cn. Okay, which means this whole quantity I can write like this: Cn to 1 plus, then this thing will be a geometric series with 3 over 4 plus 3 over 4 square plus 3 over 4 cube, etc. The whole thing is converging, so therefore this is big O of n. Yep, so this is the proof.